example here. Our first example says that this table has a number of hikers who've completed this what's called the Appalachian Trail. Does anyone know where the Appalachian Trail is?
Yeah, I went hiking.
Yeah, it's over on the East Coast. You can like hike all up and down the East Coast there. And it's the number of people that actually completed the whole thing from 1996 until the year 2000. Find an equation that models the number of hikers completing the trail as a function of the number of years, as a function of the number of years since 1996. Okay. In order to do that, well, let's first make, like we did yesterday, let's make a list of this data. So, well, right now this doesn't, we have some of the data. We have the number of hikers, which is good. That'll be like our Y. But we don't have an X. We have years, but we don't care about what year it is. We want to know years since 1996. Okay? So, like, how many years since 1996 is 1996?
0.
Okay, so if we go years since, say that's 0. How many years since 96 is 1998? 99 was 3, 2000 was 4. Okay. So to do this, let's take your graphing calculators and make a table of values that compares the year since 96, which we'll call our X value, and the hikers completing the trail as Y. And if you recall, you can get your notes from yesterday out if you want. On your calculator, remember we turned them on.
Really?
Hopefully you turn them on. Then we hit Stat, Edit. We cleared the lists, so we went up and highlighted the value and hit Clear. Highlight, hit Clear. And then typed in our data. The X is going L1, so we said 0, 2, 3, and 4. We went over to L2 and we typed in the Y, so 405, 403, 552, and 623. Okay, love it. Right, yesterday we took this data and made a scatter plot of it. Today we're going to do something new. Rather than just making a plot of it, we're actually going to get the equation of a best fit line, of a line that would go through this data the best. To do that, we can follow the directions that are on your worksheet. So to find the best fitting line, press Stat, and then hit the right button to go over to the Calculate menu. So hit Stat, and then go over to Calculate once you have your list made. Okay. Hit Stat, that brings you to this menu. And then we'll slide to the right one, so we're in the Calculate part of the Stat menu.
Wait, are these directions already?
These are the directions that are on your note sheet for today. Okay. We want item number 4, which is linreg, which is called a linear regression. Okay. You can either hit number 4 or just go down and highlight 4 and hit Enter. And it brings up this list, this function.
With the line reg.
Yep, it's called linear regression. Notice it says AX plus B in it. What do you think this is going to tell us? If we hit X, you should get something that looks kind of like this. It'll tell you what A and tell you what B are. What do you think A is going to be pretty similar to? M, and what do we say M is? In a line? The slope. So this A value is telling you the slope of the best fit line. This B value is telling you the y-intercept of this best fit line. So the equation of our best fit line for this data would be y equals 56, we'll say 0.2x plus 369.17, or round to the nearest tenth, 12.
Wait, how did you get the A? Yeah.
Okay. Again, so are we having? So is your question like, how did we get these numbers on the screen? Okay. Okay. So once we have this line of fit is extremely important because it's going to help us predict things that aren't already in our graph. So for example, it says approximate the number of hikers who completed this entire trail in 1997. Notice that we don't have any data for 1997. It's not there. We just didn't collect it.
Oh, whoa.
Right. Well, one way we can do that, we can get an estimate, would be to use our line and plug in appropriate values. So like what year, if we had to pick a number for X, what would we say 1997 is?
Year.
Probably a one. Yeah.
Years after 1996. So how many years after 96 is 97? One.
That was when I was born. And I was 1 year old. No, I wasn't.
No, you were zero.
So if you know,
Yeah, I thought it was
if we say that X is 1, and we have an equation, we could come up with a value by saying, well, what is Y when 56.2 times 1 plus 369.2? Since we have this equation in Y equals mx plus b form, plug in x equals 1 should give us a good predictor of what 1997 we think should be.
But aren't you plugging in that?
So we'll say, x is 1. So we'll say 56.2 times 1 plus,
Why do you think it's 1?
Are you plugging one to get these numbers from?
Yeah. Okay.
I'm plugging in 1 because in our data we're saying we said x is year since 1996. We're looking at 1997. So what x would 1997 be? 1. It fits in between 0 and 2 here. Now, how did I get these numbers? We got from that line of best fit. That's the whole point. That's the reason why we found a line of best fit, so we can make predictions of the data we don't already have. So we got these numbers from the linear regression. It's like your slope and your y-intercept. This is the equation of our best fit line. So if we want to make predictions for things we don't have, we'll use this line to help us do that. Since we know 97 is 1, fits in between 96 and 98, we'll plug in 1 into our equation. That should give us a good predictor of how many people hiked in 1997. Specifically, if you do 56.2 times 1 plus this, 369.2, we end up with 425 hikers. Okay.
Is it Y equals?
You could say y equals, if you wanted, 425 hikers. We'd expect that there would be about 425 hikers based on this data. Making a guess inside of our data is called making an interpolation. This is a prediction of values inside of the collected data. Interpolation is inside the data. Notice that 97 is inside of this range, so we're making an interpolation. Okay. Okay, let's take a look at the second example. This table shows that the median floor area, or the size of a new single house of the United States during this time period. Okay. This data is the approximate size of a house during this time, like a new house being built. Okay. We're going to first find an equation that models the floor area of this new house as a function of the years since 1995. Okay. So first let's get years since 1995, because that's what we want to put as our x values. So how many years since 95 is 95?
0.
How about 1996?
1.
2, 3, and 4. Okay. So let's use our calculator to make a list of this data. So we can go we can go stat. Edit a list. Let's clear our old stuff out of there. Clear the old junk. L1 is going to be our x value. X is almost always something involving time. So we'll go 0, 1, 2, 3, 4, and so on to type in the y value. Okay. Should be our table of data. Okay. Now if we want an equation, let's go back and follow that box that's at the top. Hit stat, slide over to calculate, option 4, which is linear regression, and hit enter to run it. And you should get this data as the values of for your line of best fit. All right, folks. So you've got hopefully you have your linear regression.
What do you do?
A is here. So let's write our equation of our line. So our line is what y equals 26.6x plus 1921.4. Okay. Our second question here says, this time predict the floor area of a single-family house in the year 2000 and in 2001.
Really, I hate
Okay. Okay. It says we're going to predict the square footage of his house in the year 2000 and the year 2001. Well, we found an equation that says if we take the year, we plug in the year since 95, it gives us a value. So if we want to predict how big a house is in the year 2000, well, if we could figure out how many years after 95 2000 is, then we should be able to just plug in that number. Well, how many years after 1995 is the year 2000?
5.
How many years after 95 is 2001?
6.
Okay. So if we want a prediction for the year 2000, what should we do?
Plug 5 in.
Yeah.
Plug 5 in. We'll plug it in. Okay. And we could use our calculator and say, how about 26.6 times 5 plus... So we predict this to be about 2,054 square feet.
What's under the calculator? Thank you.
So we predict the year square footage year 2000 to be at 2,054. You predict the square footage in 2001 to be at 2,081. So we predict these two values. And we got those again by plugging in 5 and 6 into the equation. Okay. Any questions about making predictions using this? All right, folks. What we just did, notice, is we made it, this time, we made a prediction outside of where our original data was. We predicted a value that that isn't in between what we have. We've made a prediction of ones in the future. Anytime we make a prediction of values that are outside of our original data is called making an extrapolation. So we're making a prediction of values outside of the given data. Okay. Is a prediction there. Okay. So extra means outside. So extrapolation is outside. Interpolation is inside. Okay. Now you actually have to do a little thinking here. Which one of those predictions from part B from before would you expect to be more accurate? Would you expect this one or this one to be more accurate? Because it's closer to our data. The first prediction, we would expect it to be more accurate because it's closer to our original data. The prediction of the value closest to the given data should be more accurate. Okay. So in our case, that's the year 2000. Should be more accurate because it's closest.
Oh, then.
So what's it say?
The prediction of the value closest to the given data should be the one that's most accurate. So like if 2000 is closer to our data set than 2001 is, so we'd expect that to be more accurate. It's kind of like when we predict the weather, like you know how like the weather seems to be the weather forecasting is more accurate like for the days that are like 1 or 2 days away than it is for like a whole week away. Like it changes as you keep getting closer. It's the same thing here. The farther away from the numbers you actually have you get, the less reliable the predictions are.
So on the one
I'm going to skip ahead and talk. Oh, actually I can't. Never mind. We got to do this whole example. Let's see if we can't do this last example here more or less on your own. Okay. So it's the Federal Communications Commission, the FCC, issues licenses for amateur radio. The table shows the number of new licenses that it's given out starting in September 2004, and it going up to January 2005. Okay. Predict the month and year in which the number of new licenses reaches 50. Well, first of all, if we want to do this, let's see if we can't get an equation. If we're going to make a prediction, we're going to want an equation. So let's see if we can't make ourselves an equation, and let's use our calculator to do that for us. So if we want to do something like we just did, if we're going to make a prediction of the years since, or like the months since this one, how about we make a quick table of the months since September of 2004. So how many months since September 2004 is September of 2004?
0.
Okay. How many months is then October of 2004? 2. December would be 3 months later. January of 2005 is 4 months later. So let's use your calculator to make a table. Stat, edit, clear, clear. 0, 1, 2, 3, 4. 203. 138. Okay. Let's go stat, calculate, linear regression. And we have a equation would be y equals negative 18x plus 197. Would be an equation of the best fit line. Again, I got that from my linear regression.
190.
So, it says predict the month and year in which the licenses reach 50. So, what value do I want to be 50 then? Y. The licenses reach 50 when Y equals 50.
I should be a teacher.
So let's figure out which X makes Y 50. Let's plug in 50 for Y. plug in 50 for y, and let's solve for x. So let's put 50 for y and solve for x. So if we say take 50 minus 197, negative 147 equals negative 18x's. Negative 147 divided by negative 18. So x is 8.16 repeating. And what does x represent? Months since September of 2004. So you'd expect that this function, or that the number of licenses reaches 50 after a little bit more than 8 months. Okay? Well, so then what month and what year is that from our original? Well, if we go back to the original, go back to here. If September 2004 is 0, October of that year is 1, November is 2, December is 3, January of 2005 is 4, what should 8 be?
Wait, you have to solve for x now?
We just did, yes. Why are we solving for x?
We didn't do that before.
We did not do that before, because before I told you something with x and I asked you to guess a y. In this question, it says predict when the licenses reach 50, or when y is 50. So when does y hit 50? Well, we got to find the x then. Well, our x is at 8.16. Well, what month would month 8 be? Well, if January is 4, February is 5, March is 6, April is 7. What's month 8? May. So this would correspond to May of 2005. Okay. The last thing for today is the zero of a function. The zero of a function is the value, is the x value when a function is 0, or when y equals 0. The zero of a function is what x is when y is 0. Okay. How would we find the zero of our function? Well, it's when y is 0. So we could say for our graph up here, we could say what if 0 now is equal to negative 18x plus 197. What was it, Austin? Excuse me.
I got 10.94.
So this is saying that the zero of our function is about 11. What does the 0 represent in here? When y is 0, what does that represent in our data? What's y? What's y represent? I'm pointing to it.
New license.
Okay, so when y is 0, what does that mean? No more new licenses were put out. So the 0 of this function is the time when no new licenses are given out or issued.